Welcome to Fred
and Amy's Math Shack.
Welcome to this second lesson on hypothesis testing. We've done an introduction. Today we're going to look at critical regions, which we'll get onto in a bit. But to start with, I want you to have a look at this question. You can't just write yes or no and it seems quite low. We need to be more scientific, i.e. you need to do a hypothesis test. So think through this. I've given you very little information, but think through it and have a go. Okay, first thing we need to do is construct our null hypothesis, and that's going to be the default that actually the coin is unbiased, because then we can do a calculation with that. And then we need an alternative hypothesis, and we're interested in whether it's biased towards tails. So you could do the probability that P is greater than a half and look at the fact that 6 tails came up, or you could look at the probability being less than a half and then focus on heads, basically. So you can either focus on heads or on tails. So I'm going to focus on heads and say biased against heads. Okay, the piece of information I haven't given that you generally are given, well, you always are given in like exam questions, is the significance level. It's this thing that we're testing against. So we are going to decide that. And we know that the smaller you make the significance level, the surer you can be if your null hypothesis is accepted. But if you make it really, really small, you might just make it too difficult. For example, we're only doing it 8 times here, so actually it's never going to, the probability of me getting 0 heads is still not going to be that tiny. So let's go with a good old 5%. That's just a good standard kind of value that you can be pretty sure about. But you could have done something different. Okay. Then we need to construct our test statistic. Let x equal number of heads thrown. And then assume h0 is true. We can then say that x will follow a binomial distribution with 8 trials and a probability of success of a half. And then that we're all set up now, we just need to work out the probability that x is less than or equal to 2, this cumulative probability. Let's just decide whether to do a list or a variable. X is 2 and is 8. Okay, and we get 0.1445. Or 14.5%. This is greater than 0.05, i.e. there was a 14.5% chance that this could have happened just due to chance. It's not that low. It's greater than our significance level. So actually, we're going to accept h0 here. The coin. You should probably say based on this evidence, because actually we don't know for sure whether it's biased or unbiased. The coin is unbiased. Just a little conclusion at the end. Okay, and that's what we did last lesson. So I'm recapping it, but asking you to have a go at it and purposely missing out things like significance level to make you think, like, what is it going to be? How do we decide it? And so on. But these are the key steps you need to write down when you're doing hypothesis testing. Okay, well actually we can take a slightly different spin on it, and here goes. We could write down a probability distribution of x based on h0, and here it is. This is using the binomial PD button, so the probability that x equals 0, x equals 3, and so on. And notice it's symmetrical, which is what you'd expect because the probability is a half, So you'd expect 0 heads to be the same as 0 tails, which is the same as 8 heads. And we can see it increasing. But here's the new question. Here's a new way of thinking about it. How many heads do we need to get? Whoops, I'm kind of giving it away. How many heads do we need to get before we have enough evidence to decide that the coin is biased towards heads? Well, it was when the probability became less than 5%, wasn't it? So if we work out our cumulative probabilities, here's our 14.4% from before. If we'd worked out less than or equal to 1, we would have got 3.5%, and less than or equal to 0, or just equal to 0, 0.4%. And what this does is this actually tells us, right, although we accepted h naughts when x was 2, okay, if it was 1 or less, we would have rejected it. And this actually forms a critical region. The critical region is the values of x that would have led to us rejecting h naughts. I say critical region, actually this is the critical region here, x less than or equal to 1. So that arrow there was not quite clear enough. But let me show you a diagram to make it even clearer. So I could have constructed my probability distribution using a sort of, it's not a line graph, it's kind of like I've forgotten the name of it actually, it's kind of like a bar chart. We're leaving gaps between it. We're just using an infinitesimal width to represent each one. And then you can actually see here's our 14.4%, and this becomes our critical region. Okay, it is the range of values of the test statistics that leads to rejection of h naughts. That's a key term from today. So it's a different way of thinking about it. It might be that we'd worked out the critical region and then seen that 2 is outside of it and therefore accepted h naught in that particular case. So you can see two ways of doing hypothesis tests. Either test the data that you have directly and see if and compare it with the significance level, or use the significance level to create your critical region and then compare the sample, and you'll be expected to understand both. The critical value is then the first value to fall in the critical region. So in this particular case, it's going to be here, 1, critical value. So the critical region, I should just add, in this case is going to be technically, I mean, we get away with if we, let me do this in red, sorry. If we write x less than or equal to 1, we get away with that because we know that x can't be negative. You might want to write x as 0 less than or equal to x less than or equal to 1 if you want to be even more precise. Sorry, that was the critical region. I've put that in the wrong place. Okay, it's up here. Critical value we then see is actually x equals 1. And that leaves just one thing. The acceptance region is the range of values that leads to the acceptance of h naught. So it's all of these here. Okay, so either x greater or equal to 2, or if you want to write it, you might say 2 less than or equal to x less than or equal to 8. So hopefully you're happy with that. It's a new way, just a new little addition to the idea of hypothesis testing. And just to say, so statisticians generally regard 5% as being unlikely. That's why we go with this 5%. Okay, because we just say it's unlikely. We're not completely sure, but it's unlikely. 1% is then very unlikely. So you're using values around this, but you might choose to use 2.5% and so on. Remember, this is called the level of significance. Okay, or the significance level, we've already talked about that. So at the 5% level, okay, I've already talked about this one. The critical region is x less than or equal to 1, since that's less than 0.05, but the other one is more than 0.05. That should be added on. But for a different significance level, okay, 1%, actually, to be really, really sure, we would have had to have got 0 heads to say that it was biased. And because actually now our probability that x less than or equal to 1 is more than 1%, it's 3.5%. So your critical region will depend on your significance level, essentially. And obviously, in this case, the best thing to do would be to do more trials, even if you got, if you didn't get 0 heads, because that's a lot to ask for a 1% significance level. Maybe you need to do 100 flips, and then you wouldn't need quite so few heads to be sure about it. Okay, there's just one other thing I need to talk about, and that is that's the actual significance level. So this, okay, there's a lot of words here, isn't there, that we've had to, lots of terminology that we're having to take on board. But the actual significance level is the probability of incorrectly rejecting the null hypothesis. So let's think about this. We might have got 0 heads just by chance. There was a 0.4% chance that would have happened. And then we would have rejected H0. But it could have been that actually H0 was true. We just happened to get 0 heads. And so we would reject it for this 1% level, even though it was true potentially. There's a 0.4% chance of that happening. So the actual significance level, when we use a 1% significance level, is 0.4%. Okay, that's that time that we've just happened to get 0 heads. For a 5% significance level, okay, there's actually a 3.5% chance that we would have got 0 heads or 1 head. And so for a 5% significance level, the actual significance level is this 3.5%. That would be the probability, again, of rejecting H0 when H0 is true. Doing the trial, getting 0 or 1 heads, but actually it was just due to chance. Okay, I hope I've explained that well. So basically, to summarize what we've done so far, we've introduced the idea, well, we first of all revised a hypothesis test. We then introduced the idea of looking at a critical region, the region where we would accept H0, the region where we would reject H0. The critical region is where we reject H0, the acceptance region where we accept H0. We've got this critical value, which is right on the boundary. And then we've got the idea that it will depend on the level of significance. And then finally, just the fact that they've got this actual significance level, that's basically the probability of us rejecting H0 when it was true. This is actually also called a type 1 error, but we're not going to talk about that anymore here. Hopefully you're happy with this so far. It's a bit of an extension to what we've done. Hopefully these terms all make sense. Here's a second example on critical regions. So we're given the null hypothesis, we're given the alternative hypothesis, we're given the distribution. We don't need to worry about any of that. All we need to focus straight on is finding the critical region. And that's going to be similar to how we did it before, but we're not given a number of successes to compare against. So this time it's to the right, and we're going to test, therefore, values to the right. We're going to test greater or equal to 6 to start with, and then maybe greater or equal to 5, and we'll see how we get on from there. So greater or equal to 6 is actually going to be the probability that x equals 6. Therefore, the quickest way of doing this is going to be to use the PD button. And we get a very small answer, 0.00183. And I should probably just add that this is 5 less than 5%. So it's going to be in the critical region. Yeah, because it's such a small possibility of happening. If it does happen, then I would reject H0. Yeah, I think it helps to just keep a list of that as you go, because then we'll spot when it changes over. Okay, sorry, back. Right. Then for greater or equal to 5, hang on a second, we need to use our knowledge and do 1 minus the probability that x is less than 5, which is the same as less than or equal to 4. So I'm going to use the CD button. But put 4 in here. Whoops, sorry. 4 in here. Okay, I get that. I'm going to store that. We can see it's going to be less than 5% because it's more than 0.95. But let's take our time. You could make a direct comparison with 0.95 to be fair, but I'm not going to do that here. Okay, 0.0223. So this is also less than 5%. It's going to be in the critical region. And then finally, I say finally, I mean the next one, I happen to know that this is going to be more than 5%. You can kind of see that it's growing quite quickly there. So just to say, I suppose, like it is okay to compare it with 0.95, and maybe you'd argue that would be a bit easier. I'm just going to stick with it this way. Okay, now we're looking at x is less. We're going to do 1 minus x less than or equal to 3. And we get 1 minus this. But you can see it's going to be more than 5%. Okay, 0.117, which is greater than. My 7s and my greater thans always look really similar. I'm sorry about that. Greater than 5%, so not in critical region. Yeah, this does link back to what we've done previously. If you had got this observation greater, if you had got 4 as an observation, then you would accept H0. There's not enough evidence. There's enough probability of it happening at chance. If you got 5 or more, you would reject H0. So the critical region is actually x greater or equal to 5. You can say that it's less than or equal to 6 as well if you like, but that's good enough. Or you could say 5 or 6. Critical value is then x equals 5. All right. Quite a lot to do there because of this 1 minus, but it is the same principle as before. Just the last bit, state the actual significance level of this test. Remember, this is the probability of rejecting. It's worth like writing this down every time you sort of see this question. Rejecting H0 when it is true. So actually, it's a probability of us getting 5 or 6 just by chance when actually, because then we would reject H0 when actually H0 is true. So it's this one here. It's the probability that's just on the cusp of the critical region. It's 0.0223, or you might write 2.2% to a percentage in just 2 significant figures. Okay, have a go at this question. This is kind of the full thing now. And interestingly, it's a hypothesis testing question about hypothesis testing. So, part 1. H0 is going to be that the probability is still 0.8. H1 is going to be, because we're saying they're now underperforming, it's going to be that it's gone down. It's less than 0.8. And the test statistic is going to be, we're looking at a test on 20 students, it's going to be the number who passed the test or the assessment. So part 2, we're going to assume H0 is true. X is going to follow a binomial distribution, 20 trials, 20 students we're looking at, and the probability of success is going to be 0.8. And then I'm going to need to work out my critical region. Okay, because it's this like less than one, it's just so much easier, to be honest, because you can just use the commutative distribution. So let's do a list. It's probably going to get, because the probability is so high, actually, we're going to need to have a lot of students. The critical region is still going to be, it's going to include a lot of students. So I think I shouldn't have started with 0, but I've done that. Because I can see in the next bit of the question it's talking about 12 students, I think I should definitely go up to 12. In fact, I should have started before. I say, okay, let's just, there's no harm in just finding out a load of them. Okay, 20 trials. And we're going to get some really small probabilities at the start. Okay, shouldn't have worried about those. But here we've got 8%. Aha, this is making sense now. I've got 13%. So I can see that the probability that x is less than or equal to 12 is 0.0321. So this is greater than 5%. And it's going to be, sorry, less than 5%. It's going to be in the critical region. Probability that x is less than or equal to 13 is where it goes over 5%, 0.0866. And this is greater than 5%. I need to be careful, don't I? So when I say in critical region, I'm saying that x greater or equal to 12 is in the critical region. But I'm basically saying here that 13 not in critical region. I hope this is making sense. And that's enough then. So our critical region is going to be x less than or equal to 12. Okay. And then part 3, well, we are, if only 12 students pass, then we are actually in the critical region. So we would, so 12 is in the critical region. Reject H0. The probability of them passing has decreased. Okay, that's the key bit. That's like the exam bit. I added number 3 on because I wanted some suggestions really to make you think about it. What should they actually do? Now we've got to remember, this is a new teacher. They've only just hit that been in the critical region, so it's not that bad. Maybe it was a weaker class. Maybe they hadn't worked hard enough. Maybe it was the teacher's first time through teaching hypothesis testing. Maybe they should watch this video. Maybe the head of maths, they should just give them some guidance on hypothesis testing. But there could be lots of reasons. Maybe they mark more harshly, and so than the previous teacher did. The previous teacher might not have been quite so rigorous, and just given the marks here or there. So I suppose what I'm saying is, don't just get rid of the teacher. And hopefully you're happy with this. So another example of critical regions, and then using a value to see if it's in the critical region or not. Okay, one more example to try. This time, I want you to do the question using two methods. First of all, the method that we discussed today, finding the critical region and then deciding whether or not the value's in it and making your conclusion. And the second way, just revisiting last lesson and testing the probability directly. Okay, in this situation, we first of all construct our null hypothesis. And that's going to be that the probability remains as 0.4. Our alternative hypothesis is it talks about the fact that there's an increase in the proportion, so it's going to be p is greater than 0.4. Construct our test statistic. Let x be the number who travel by train. Okay, and then assume, this is the same for both methods, by the way. Assume h not true. X will follow a binomial distribution with 16, because that's the random sample we're looking at, 0.4. Okay, this is where we split into two different methods. So method, it's a new method here. Okay, we need to find out the critical region, so where basically we cross from above 1% to below 1% or vice versa. In this case, we're looking to the right, however, so actually if we use the cumulative distribution, we need to look at that 99%. So let's just head over there and see what happens. So menu, distribution, binomial CD, and I'm going to do a list. Okay, and it talks about 11 of them, so maybe I try some values around 11. So 9, 10, 11, 12, and 13. N is 16, and P is, I've forgotten, 0.4. Okay, and we see that this here is below 99%, and then it goes above. So the probability that x is less than or equal to 10 is 0.9808. So what does that mean? That means that the probability that x is greater or equal to 11 is going to be 1 minus that. We'll work that out in a second. We'll just store it in our memory for now. And then we've got the probability that x is less than or equal to 11 is 0.9951. So then to get the probability that x is greater or equal to 12, we can do 1 minus that one. So let's store this into another bit of our memory. Okay, 1 minus a is going to give us the first one, 0.019. Put another digit in, 91. And this other one's very small, 0.00489. So just to then add, this is going to be greater than 1%. So it's outside the critical region. When I talk about that, I mean 11 is outside the critical region. And this one is less than 1%. So 12 is inside the critical region. And therefore, the critical region is going to be x greater or equal to 12. In our case, 11 have said they now travel by work, so this is outside the critical region. 11 is outside the critical region. So accept H0. It's in the acceptance region. We don't have enough evidence to say that it's gone up. Actually, we just need to then write a conclusion. There's not enough evidence of an increase. Okay, brilliant. We've done this problem using critical regions. Okay, let's just take a step back and do it for this other method we had from last lesson. Method 2, and that actually is just to directly work out the probability that x is greater or equal to 11. And that is then 0.0191. And actually, we just need to then say that this is greater than 1%. And from that, we can simply go to here. So why do it the left-hand way? Because yes, there was a lot more involved, especially in this case, because it was a greater than, we had to do 1 minus and so on. Yeah, my argument would be, if you see a question like this, then use the second method that we looked at previously. However, being able to calculate the critical region is a useful thing, because you might in theory, in practice actually, I should say, you might actually work out the critical region before you actually undertake your sample. You might say, I'm going to have 16 people that I'm going to randomly sample. Here's the critical region, and then as soon as you've finished your sample, you know whether you accept H0 or H1. But in an actual exam question, in this case, it would be quicker to use the second method, obviously. At the same time, you will be expected to get the critical region, and questions might say calculate the critical region, and it is a useful thing to be able to calculate as well. So I suppose if I'm summarizing this lesson, it is, don't forget what we did last lesson, because it comes in really useful in situations like this. But make sure that you can calculate the critical region as well for probabilities that are less than the value that we think it might be, or greater than. Bit more work involved on the latter. Okay, make sure you are setting it out carefully. It's really important. I've just constantly, I've not skipped steps every single time. I'm just going through the steps, and that will just help you memorize the techniques and understand them. Thank you. I hope this is all making sense.